Magnetic moment. Magnetic properties of material are due to electrons in the atoms. Okay. In atoms, the electrons have angular momentum and spin angular momentum. So this is the electrons which are revolving around the nucleus, center of the nucleus, which is having angular momentum as well as spin angular momentum. Okay. The orbital as well as spin angular momentum are quantized and gives rise to orbital magnetic dipole moment. So due to this, what happens? There is magnetic dipole moments is occurring. Okay. To the spinning of the electron around the nucleus, what happens? Magnetic dipole moments occurs, as well as orbital magnetic dipole moment and spin magnetic dipole moments are occurs. The vector addition of all these two magnetic dipole moment gives rise to a resultant dipole moment, okay, of the specimen. So vector addition of both the dipole moment gives us the total, okay. Total means magnetic dipole moment of the whole specimen. So in this figure, this is the electrons which is at a distance r from the center and which is revolving like in this direction. And opposite is the direction of the current. You will see this this is the I symbol here. So this is the direction of the current, which is opposite to the movement of the electrons. If the resultant magnetic dipole moment produces a magnetic field, the material behaves like a magnet. Okay. So due to this dipole moment, what happens? It produces a magnetic field. This what happens due to magnetic dipole moment. Magnetic field is generated, and material behaves like a magnet. Okay. When material placed in external magnetic field, the magnetic dipole moment of the electrons are modified. When you place this material, what happens? If you place this material in the external magnetic field, the magnetic dipole moment of the electrons are modified. Okay, it will get changed. Types of magnet. Classification of magnetic and non-magnetic material. Diamagnetic material. It includes copper, zinc, mercury, gold, silver, and others. So these are diamagnetic materials we have. They becomes weakly magnetized. So when you apply some magnetic field to these materials, then what happens? They are weakly magnetized in the opposite direction to the magnetization field. So these are the diamagnetic material we have. If you apply some external magnetic field, their dipole moment is opposite in the direction of the magnetic field. In case of diamagnetic material, this is the case when magnetic field is zero. External magnetic field is zero. So, and this is the case when you apply the external magnetic field. All these dipole moment of this material are aligned opposite in the direction to the that of the external magnetic field. Such a material are called as a diamagnetic. In case of paramagnetic, at when there is no any field is there, then you will see the all these dipole moments are in the random direction. One is here in this direction, one is in this direction, one is in this direction. When you apply some external field, what happens? All the dipole moments are aligned in a particular direction. Okay. They are aligned in a particular direction. In case of ferromagnetic, all the dipole moments have particular orientation, particular direction. But as soon as you apply the external magnetic field, they are aligned according to the direction of the external magnetic field. So this is the difference between all these three magnetic material. Now we are seeing diamagnetic material. These are the materials that are showing the diamagnetic properties. The atoms does not possesses any net magnetic dipole moment. So at the beginning they are not possessing any dipole moment. Okay. When diamagnetic material placed in external magnetic field, magnetic dipole moments are developed, which are directed opposite to the external field. Here you will see that they are at the start there is no any dipole moment is here, but as soon as you apply the some field, the dipole moments occur and which is opposite to the that of magnetic field. the magnetic flux density inside the material decreases. Okay. The magnetic susceptibility is negative for diamagnetic material. So magnetic susceptibility is negative. So this may become as a MCQ. The magnetic susceptibility is what? Negative, positive, or no any value for the diamagnetic material. So this may be one of the MCQ type of question. The induced magnetic dipole moment disappear on switching of the external field. They say as soon as you remove the external field, what happens? The dipole moment is get destroyed, and they are come at their original position. Means there is no show of the dipole moment occurs as soon as you switch off the external field. Non-magnetic materials are air, paper, wood, and plastic. So next topic is Langevin theory of diamagnetism. So according to this theory, the orbital motion of electrons gives rise to the diamagnetic properties. Okay. So the electrons which are revolving around the nucleus gives rise to diamagnetic properties. The orbital motion of electron gives rise to magnetic moment. So we have seen that which are revolving around the center of the nucleus. This is the orbital motion it is having, and it is giving out the magnetic moment. Okay, orbital motion. The magnetic moment of all electrons cancel each other as they are in the random direction. Okay, so all these electrons, when they are in the random directions. So here you will see they are in the random direction. They are cancelling each other. When the magnetic moment of all electrons are cancel each other as they are in random direction. When external magnetic field is applied, what happens? Orbital motion of the electrons in atoms are altered. Okay, it causes current loop in the to develop. So due to which what happens? Current is generated. Current loop is generated there. The magnetic moment produced by these induced current loops are opposite to the applied field in accordance with the Lenz's law. Whatever current that is generated which is opposite to the magnetic moment of the electrons. This is the equation for the Langevin theory of diamagnetism. So in the exam you will ask which is the equation for the Langevin diamagnetism. So this is the correct answer. So in this equation, what is this is Xi is equal to n into Jd square mu 0 upon 6m into r square. This is the equation. This is my minus sign of the whole. In this equation, what is mu 0? Mu 0 is the permeability of free space. Okay. What is n here? N is the number of atoms per unit volume. How many atoms are there in the specimen of the material? So that is the number of atoms per unit volume. Okay. Z is the number of electrons in an atom. So you know the number of atoms, then you can able to calculate number of electrons also. E is the charge of on electrons. E क्या है charge? M is the mass of the electrons, and R is the mean square distance of the electron from nucleus. So R is the distance. This is R square. Okay. So you know all the values, then you can able to calculate the value for the Xi. Okay. All these value you know, this is constant, electron charge is constant, only these are changing here. Then next article is paramagnetic material. So we are talking about the different types of material. Paramagnetic now. Which are the paramagnetic material? Aluminum, platinum, manganese and chromium. हेलो, समझ में आ रहा है सबको? हेलो स्टूडेंट्स.
Yes, sir.
ओके. So paramagnetic material are aluminum, platinum, manganese, and chromium. Okay, they become weakly magnetized in the same direction as that of magnetizing field. The permeability is slightly more than 1. So here you will see that they are weakly magnetized. As soon as you apply some magnetic field, what happens? They are aligned in the direction of the magnetic field. This is the direction of the dipole moment. Okay. Each atom possesses a net magnetic dipole moment. In absence of external magnetic field, these dipole moments are randomly oriented, due to which net magnetic dipole moment of material becomes zero. So at first they are randomly oriented, so that's why momentum is zero. When placed in external field, what happens? Dipole align with the field, which leads to increase in magnetic flux density. So magnetic flux density increases as soon as you apply some external magnetic field given to this material. This material. Paramagnetic material placed in a non-uniform magnetic field, they move towards the region of stronger magnetic field. So field lines are able to pass through this material. In a diamagnetic, field lines are not able to pass, but these material allow the some magnetic field lines to pass through them. Net magnetic moment lost when external field is removed. As soon as you remove the external field, again they will randomly oriented. When you remove the H, what happens? They will again change their direction. They are not in the direction of the applied field. They will randomly oriented as soon as field is removed. This is the paramagnetic. Now the next article is susceptibility is very small and positive. Langevin theory of paramagnetism. Next article. So the magnetic dipole moment align in the direction of the magnetic field. We know this. When you in the direction of magnetic field, when you apply some external magnetic field, there dipole moments in that direction of the external field. The random thermal motion tends to disturb this. The random thermal motion tends to disturb this alignment, making the effect temperature dependent. So what happens if you increase the temperature of this material? What happens? This alignment get disturbed. They are not aligned in the particular direction. It means their magnetism get destroyed as soon as some external temperature is given to this material. So this is the disadvantage of the paramagnetism material. Okay, the magnetism will get destroyed as soon as some external temperature or some heat will be there. That's why this is the disadvantage of this material. What is the equation for this? Langevin theory of paramagnetism. The equation is I is equal to mu 0 mu m square into capital N upon 3 kT. So all this value is nothing but your C, capital C upon capital D, C upon D. See this whole value becomes okay. This whole value mu 0 C is what? Mu 0 mu m square into capital N upon 3K. What is C here? C is nothing but mu 0 mu m square N upon 3K. Only T is not there. Okay. So what is this C here? C is the constant called as Curie constant. T is the temperature. K is Boltzmann's constant. We know that value. Mu m is the magnetic dipole moment. N is the number of atoms per unit volume. Mu 0 is the permeability of the free space. So in the exam, you will ask what is the Curie constant. The correct answer is this one. This is the formula for the Curie constant. Or you will ask what is the Langevin, according to Langevin theory, what is the equation of paramagnetism? What is the equation for the paramagnetism? This is the equation for that. Hence, susceptibility of paramagnetic material यहाँ तक हुआ था ना?
हाँ सर।
ओके. Now the next is West's theory of paramagnetism. What is West? West is the name of the scientist. West assumed that in addition to the externally applied field, the internal molecular field produced by neighboring molecules also acts on the magnetic dipole moment of any molecule. So other than externally magnetic field, there is also one of the neighboring magnetic field that is acting on the molecule. According to him, the susceptibility of the magnetic material is Xi is equal to mu 0. Only what is the change here? Capital T minus theta c. Rest of the equation is as it is. So it is as it is from the that of the paramagnetic susceptibility. Xi is equal to mu 0 mu m square n upon 3 kt. Only this t value is change here. This theory. So in this equation, what is here? Mu 0 is the permeability of free space. Mu is the magnetic dipole moment. C is Curie constant. K is Boltzmann's constant. So all these are constant value. So what is changing here? Absolute temperature. N is the number of atoms per unit volume. This N is number of atoms. This equation is called as the Curie-Weiss law, and theta c is the paramagnetic Curie point. So what is this? Theta c is the paramagnetic Curie point. This law, this equation is called as the Curie-Weiss law. So in the exam you will ask what is the Curie-Weiss law? The equation for that. Just change the temperature here. Add the subtract theta c value from capital temperature T. Now the next next article is ferromagnetic material. So which are the ferromagnetic material? Iron, steel, nickel, cobalt. These are permanently get magnetized as soon as you place them in the external magnetic field. Ferromagnetic material we have. They are aligned in the direction of the external magnetic field when you place them in the external magnetic field. When you apply some external magnetic field, they are oriented dipole moment oriented along the direction of the external field. They become strongly magnetized in the same direction of the magnetic field with a high value of permeability. The atoms of ferromagnetic material moment have a large dipole moment. The unmagnetized specimen, these magnetic dipole moments are randomly oriented, due to which the net magnetic dipole moment of the sample is 0. When specimen kept in external magnetic field, these dipole moments get aligned in the external field to give the specimen a large net magnetic dipole moment. When you place this material on, as I told you in the shown in figure, when you place this material external magnetic field, so alignment is happening there. On removing the external magnetic field, the material retains the magnetic properties and material shows permanent magnetism. So they are this orientation of this dipole moment are not disturbed when you remove the external field. But in case of paramagnetism, this orientation of the dipole moment get disturbed. Okay, so this is the difference between paramagnetic and ferromagnetism. The material loses its magnetic properties on increasing the temperature. Again, you will see that as soon as you give some temperature, then this orientation of dipole moment is get disturbed. They lose their property of the magnetism. Okay. Up to Curie temperature, beyond which it becomes a paramagnetic. So, the Curie temperature is the temperature up to which this magnetic moment are showing the means the temperature at which these magnetic properties of this material are lose out. It is called as the Curie temperature. and beyond this Curie temperature, it becomes paramagnetic. Okay, so it have large magnetic susceptibility. The magnetic susceptibility changes with the temperature above Curie temperature according to the Curie-West law. Okay, this may be one of the MCQ type of question. The magnetic susceptibility changes with the temperature above Curie temperature. कब change होता है above the Curie temperature? So this is the correct answer. Or Curie-West law. What is the Curie-West law? So you must remember this point. So susceptibility is I is equal to C upon T minus theta. In this, C is the Curie constant, theta is the Curie temperature. Theta what? Theta shows the Curie temperature at which magnetic properties will get disturbed of the ferromagnetic material. Now we'll see the applications. समझ में आ गया सबको? Hello?
Yes,
Hello?
sir.
Okay. Now we will take the application. What are the applications? Application of magnetic recording and readout. So we are using magnetic properties or dipole moment for the storing of the data or in the magnetic tapes. Earlier we are using this magnetic tape to store the songs or movies. Okay. So we are using this property of magnetism or orientation of this magnetism dipole moment for the storing of the information, storing of the data. Magnetic recording. So we are recording the things. Our voice can be able to record here on the magnetic tape. So this is the black portion shows the motion of the tape. So this is the motion of the tape. Earlier these dipole moments are randomly oriented, but as soon as you give some external magnetic field to this signal, we are sending the signal through this wire here, so that these are generating magnetic field. So this is the magnetic field is generated here, and there is some gap between the tape. This is rotating tape we have, and there is some gap between the this magnet and this rotating tape. Some air gap is there. But due to this magnetic field, what happens? Due to this blue color shows the magnetic field lines. So due to this magnetic field lines, these dipole moments of this magnet, the magnetic layer is applied on the plastic. This is the plastic film on which magnetic layer is applied. That is magnetic emulsion on the tape. So this on the plastic tape we had applied a magnetic emulsion. So there is some these are the dipole moment and which are in randomly oriented on the magnetic tape. But as soon as they are passing through this magnet, what happens? They are aligned in a particular direction, and accordingly the signal of the electrical signal is stored on this magnetic orientation. Okay. So we are using this technology earlier for storing of the information in the magnetic field. Magnetic recording based on the concept that data in the form of sound or optical signal on the in the digital form can be converted into electrical signal. So we are converting sound and optical and other signal into electrical signal, which is then turn used to produce magnetic field. Okay. First of all, we are converting sound signal into electrical and then electrical into the magnetic. So due to this magnetic field, what happens? It orients the magnetic moment in a ferromagnetic material. For this, coil is wound on a ferrite ring with an air gap as shown in figure. So this is the ferrite ring we have. So this is the wire through which we wound here. So electrical signals are due to this electrical field. What happens? Magnetic field is generated on this ferrite magnet. A magnetic tape consists of coating of ferromagnetic material on a plastic tape is made to move on the air gap. The input signal converted electrical form is fed to the coil. We set up the magnetic field in the ferrite ring. As I told you, there is electric field is generated, and due to this electric field, magnetic field is set up in the ferrite ring. As the air gap has less permeability than magnetic moment, just below it, most of the magnetic flux completes its path through the magnetic material. The flux align the randomly oriented magnetic moments according to the applied signal in horizontal direction. So all these magnetic field orient the magnetic moment in a particular direction here. You will see all these moments which are random, they are aligned in a particular direction. And the data or signal is get stored here. Okay. So we can able to again we can whenever you allow to pass this step again through this coil, again there is a reading reading of the signal is taking place. Again this magnetic field is convert that signal into electrical and electrical to the sound. Then we can able to hear the things. So we can store the information on this magnetic step for very long time. But only the disadvantage is that this is a sequential form. You can't able to whatever song if you song or any voice if you store on this magnetic tape, it will play sequentially. Means you can't change the position of that song. Okay. Once this first song will get complete, then second song you can able to hear. So this is the disadvantage of this storage. When second song and then third, if you want to play the fifth number of song, it is not possible for to you. You have to hear all the four songs, then you can able to hear the fifth song. So this is the disadvantage of this magnetic recording. It's stored. This method is called as longitudinal recording, as bits are magnetized along with the length of the tape. For a small magnetic field, the number of dipoles getting aligned with the applied magnetic field increases with the magnitude of the field. Okay. This is used in analog recording as in case of audio recording. So we are using this for the analog recording or audio recording. For large magnetic field, most of the magnetic dipoles get aligned with the applied magnetic field. As a result, number of magnetic dipole moments get aligned with the applied magnetic field does not change with the field. This condition is used in digital recording. To read the data, the tape is made to move under a read head. So there is writing head and reading head is there. One is writing, one is reading head. Okay, in this magnetic recording. To read the data, the tape is made to move under the read head, which is similar to the write head. The flux associated with the ring changes as it moves over the aligned magnetic moments and induces current in the coil. Again, there is generation of the current takes place when this tape is allowed to move. There is magnetic field is get changed. So due to which what this current is induced on the coil and signal is generated here, and we are able to read or hear that song or that information. Another is the storage is the floppy disk. So this is a floppy disk. This is a magnetic tape that we have studied right now. Then floppy disk is also one of the storage. Then hard disk. Data presented uh, data presented as a magnetic spot. Magnetized spot means 1. Absence of magnetized spot means 0. So all the information stored in the form of 1 and 0 on the magnetic disk. Read converts the magnetized data into electrical impulses. Okay, and write convert the electrical impulses to magnetic spot or disc. So read write head is there, uh, which is for the reading head is used to convert the data into electrical impulses, and writing head convert the electrical impulses into the magnetic spot on the. This is the working of the floppy disk. Sorry, this is actually magnetic tape or magnetic impulse. This is not correct. I have taken this magnetic tape. Now we are talking about the floppy disk. So this is the floppy disk we have. This is the external covering. This is the index hole and vinyl dust jacket. So this is the vinyl dust jacket we have, and floppy disk is actually in the circular form. This is just a jacket, and all these floppy disk contains tracks. Various tracks are there. All the information or data stored on this track. All this track contains thousands of sectors. Okay. Figure for the So all these floppy disk contains tracks and sectors. So these are the sectors where the information is get stored. It is made up of the plastic disc with a coating of magnetic material on it. So just like magnetic tape, we are using the magnetic coating on the plastic disc. Only the thing is that this is in circular nature. That is the strip in magnetic tape. The disc is enclosed in a thick plastic covering with opening for the read write head. So there is some opening for the read write head. Okay. There is opening for the read write head in the plastic covering. The opening remains closed until it is inserted into the floppy disk. The it divided into circular concentric tracks as shown in figure where the data is recorded. The disk is divided into sectors as shown in figure. Three sectors are there and tracks. These are the rings, nothing but the tracks, and sectors are there on between these two rings. As this is rotated and right head align in the magnetic moment on the tracks as it passes over them. So there is writing of the data takes place on this magnetic disc. The movement of the head is controlled by a servo mechanism. So there is motor is there. So this motor rotate this disc when you insert on the floppy disk. Of the floppy disk occurs by the servo motor. The movement of the head is controlled by the servo mechanism. It also has a small storage capacity up to 1.44 MB. So earlier this floppy disk was we are using for the storage of the information. Maximum capacity is only 1.4 MB. This is very small actually, but you can store your Word file, Excel file on this disk, but not for it is not used for any kind of uh, very high data consuming such as movies or songs. Only documents can be able to store on this earlier. This is the floppy disk we have. The size of this floppy is 3.5 inch. With all large files can be able to store up to high capacity portable disk. This is the high. This disk is a very high capacity, which can able to store 120 to 200 MB of data. Okay, but only the things is you need to purchase this external portable device to get the data from the floppy disk. Okay, so that's why it is very costly. So this is the figure of the hard disk. Now we will see the hard disk. What is hard disk? Hard disk contains number of disks on which we are storing the information, and again we are getting the information. So this is the hard disk we have, and this is the spindle which rotate this all the disks. Okay, this spindle rotate all the disks, and this is also read write head. This is the read write head we have, and this is the axis of the arm. So this is also get rotated. So this arm is also rotated, and this is also rotated, and we are storing the information as well as we are getting the information. You will see that all the disks are rotated. There are number of disks are placed on this spindle. So all disks are rotated at the same time. Similarly, all these axis arm are rotated, and they are moving on these tracks. So all tracks are here, as we show in the properties. There are tracks are here, tracks and sector. So this head is used to get that information from particular track. Okay, this is called as a hard disk. No, in all the PCs we are using the hard disk. Hard disk magnetic disk with floppy disks, but with a large number of disks. Number of disks are there. Large number of disks mounted on a common central shaft are coated on both the side of the magnetic material, except the two outermost disks, which coated on the inner side. The read-write head is provided per surface. So this read-write head is provided for each floppy disk. Okay. So all the disks given the read-write head. Each disk is divided into tracks and sector. The right head align the magnetic moment on the tracks as it passes over the tracks. So this contains magnetic material on this disc. So there is a dipole moment is happening when signal is came. If you give some this signal to this read write head, what happens? These electrical signals are given to this read write head, and there is magnetic field is generated. So due to this magnetic field, what happens? All the dipole moment of the material will get change their orientation, and this is how the information it gets stored here. Okay, at a particular point, at a particular track and sector. Vertical alignment of magnetic moment is used for higher storage density. Data can be stored on both sides of the disk. So from top and bottom, both the sides there is magnetic layer is there. In case of floppy disks, only on the top side there is magnetic material we are placed. But in case of hard disk, from both the side of the disk, from top and bottom, there is a magnetic material we have, so that more number of data can be able to store on the hard disk. Capacity capacity up to 5 terabytes can be we have of the hard disk. So these are the some of the points of the hard disk. Driving capacity up to 440 GB. Data found to be 9.5 millisecond. So within a very small time, we can able to get that data. Compared with floppy disks, it requires very large time. Spindle spin between 5,000 to 15,000 RPM. This is the speed of the rotation of the disk. Within 1 minute, how many rotation are there? 15,000 rotation. So it contains two sides, top and bottom. Two or more aluminum platters are there. Primary storage device in computer. So this is a primary device in the computer. They are of various sizes, portable. Generally, they are not portable. It means you can't able to carry this anywhere else. You have to take a whole setup with you. Then and then you can able to use this. Removable hard disk available in the PC. Rigid platter coated with metallic substance. Figure of the hard disk pack. So this is the figure of the sectors. So this is the tracks we have of the properties, and this is the sector we have particular. So this line shows the various sectors on which data is get stored. So data is stored on the track as well as in the sector. So these are aligned one over the another here. Logical layout of the disk cylinder. So ferrite. Ferrite is a non-metallic material that have ferromagnetic properties of iron. They have a high permeability. However, ferrite is a non-conducting ceramic material. The common application include ferrite cores. Common application of ferrite are ferrite cores in the coils for RF transformer, ferrite beds which concentrate the magnetic field of the wire on which they are struck. Okay, so this comes to end of your this chapter. These are the I have already taken all this definition of your chapter. That is the magnetic.